Welcome to watch this video. My name is Yu Li. I'm a PhD student from the Nanoengineering and Spintronic Technology Group in the University of Manchester. Today, I'm going to show you one of our recent theoretical work. In brief, we find during the Bloch-point dynamics in chiral magnets, an emergent electric field can be generated. This field has a substantial magnitude, which is in the order of megavolts per meter, and also oscillates with the frequency in terahertz range. This work is published on Physical Review Research, and the paper is open access, which means everyone can get access to the main text with details free of charge. Everyone is welcome to read, share the feelings, and communicate ideas with other people. Includes but not limited to who loves skyrmions and spintronics, especially you. Before we move forward, I would like to gratefully thank all of our collaborators, Leonardo, Hans Benjamin, and York from the ETH Zurich, Mihalis from the University of Louisiana at Lafayette, Niels, also from the University of Manchester, and my supervisors, Jim and Christophorus. In this video, I will start with an introduction of chiral magnets and magnetic skyrmions, and show how the metamagnetic transitions occur in the skyrmion lattice. Then during this process, the annihilation of single skyrmions is mediated by Bloch-point dynamics, and will give rise to an associated emergent electric field. Crucially, by engineering a notch structure, we also show the feasibility of tuning this electric signal by manipulation of Bloch-point dynamics. In general, a chiral magnet usually stacks with a non-central symmetric structure in bulk system, such as B20 type manganese silicon and iron germanium, etc. In the lattice, one heavy metal atom is strongly coupled with two ferromagnetic atoms. Then, by virtue of such unique atomic arrangement, the spin-orbit coupling raises another energy term called Gyro-Lushinsky-Moriya interaction. The DMI prefers neighboring magnetic spins S1 and S2 to align in a perpendicular direction in order to minimize its energy. And we've already known that in magnetic materials, the Heisenberg exchange interactions prefers two spins to align in parallel. Therefore, when we are considering the combined effect of these two interactions, magnetic skyrmion will be a stable solution in such a magnetic system. In a perfect skyrmion, spins in such textures are pointing upwards, and when we move away from the center, spins are smoothly twisting and rotating outwards until fully point downwards. Such textures have robust stability in theory and cannot be continuously unwound into a ferromagnetic state. In the view of topology, here's a very simple example to help you better understand how it works. Imagine you have a rope with a knot, and you are going to untie the rope or retie the knot in another way. Maybe you should break the knot into lots of threads and then build them together. Unfortunately, either way will take you great efforts, and it seems like an impossible mission. Let's go back to the magnetic world. If we are going to transform the domain wall with a clockwise chirality to an anti-clockwise chirality, if we assume the magnetization field is continuous, it will be encountering an infinite energy barrier. Then in two dimensions, this property can be quantified by the topological charge, and also for a single skyrmion, if you make a spatial integral based on this equation, you'll normally get quantized topological charge equal to +1 or -1. In our previous work, we used micromagnetic simulations to make an analysis on the transitions of a skyrmion lattice. These simulations were carried out by MUMAC3 packages. When we apply a magnetic field antiparallel to the core of the skyrmions, when the field increases, the skyrmion shrinks, and finally at around 1.5 Tesla, all the skyrmions annihilates into ferromagnetic states. And in very recent, people from experiments also found similar phase transitions in iron germanium materials. It could be a good correspondence of numerical simulation and experiments. Such phenomenon can be easily explained, as spins tend to rotate parallel to the magnetic field in order to minimize the Z-man energy. So the ferromagnetic state will be a ground state at a high magnetic field, and all the skyrmions will annihilate anyway. However, on the other hand, the dynamic process of single skyrmion annihilation has not been discussed yet. So it will be very interesting to see how the annihilation happens, not only the visualization of dynamic process. It also helps to explore the underlying of energy landscapes between two states. Moreover, such process is relating to the unwinding of topological charge in the trivial state. Here we pick up a slice of the skyrmion lattice. In the cross-section view, we can find a three-dimensional space. A single skyrmion exists as the skyrmion tube connecting both top and bottom surfaces. As the distribution of the DM energy is non-uniform through the layer, with higher value near the bottom and a lower value at the top. Therefore, the skyrmion firstly shrinks from the bottom and unzips towards the top surface until the tail fully leaves from the magnetic materials. Then we plot the magnetization as vectors and the topological charge density as the background color. During the annihilation of such skyrmion tube, we could find the configuration near the top surface remains as skyrmion-like structure, while the skyrmion near the bottom gradually unwinds into topological singularity, a Bloch-point. And in the view of topological charge, these two configurations are equivalent. Now the mystery of such dynamic process can be understood. It starts from the transformation of the skyrmion-like texture to a Bloch-point. After that, as Bloch-point moves towards the top surface, the whole skyrmion tube gradually unwinds into the ferromagnetic state until fully disappears when the Bloch-point is pushed out of the top surface. In our case, as we are discussing a rapid dynamics on the spatial scale less than 100 nanometer and the time scale of several picoseconds, we also conducted atomistic simulations by an open source package, Spirit, in order to reach a full atomistic resolution. Because we are exploring a non-defect structure with regular atomic arrangement, when Bloch-points pass by the neighboring spins, they will experience a periodically varied energy barriers and potential wells. So it will never move in a smooth path, but constantly oscillates in all the x, y, and z directions. Here we should remember all the fascinating phenomena are based on numerical simulations, and we are really looking forward to the validation in reality, like how we could detect the Bloch-point during the skyrmion annihilation process, and even detect these oscillations accompanied by its ultra-fast motion. Here we find the theory. Imagine if we have a magnetic skyrmion placed in the center of the screen. Then there is a free electron. When it travels through the whole texture, it will be interacting with local magnetization, and the magnetic moment of the spin will try to adjust towards the same direction. And then, if this skyrmion texture also changes with variations in space and time, we could analogy to the Faraday's law, and it will produce an effective Lorentz force on the electron, which will radiate a field called the emergent electric field. It is originated from the spatial and temporal change of the local magnetization. Based on this equation, we calculated the effective electric field induced by the Bloch-point propagation. Our calculation also shows the emergent electric field is linearly dependent to the Bloch-point velocity. As the velocity is in the order of km per second, the induced electric field is around several megavolts per meter. Such value is extremely large. Let's make comparison. The magnitude of the dielectric breakdown in vacuum is around 3 megavolts per meter, which is very close to the maximum value here. And this is solely from the Bloch-point propagation. And as we mentioned before, we are exploring a perfect lattice, and the Bloch-point will experience quite similar energy barriers when moving through the layer. As a result, we will find regular oscillations. Let's make a fast Fourier transformation. And the fundamental frequency of the signal lies in the terahertz range. Maybe it's still too early to talk about the application of this phenomenon. However, if we are considering its magnitude, it won't be a stupid idea to talk about the detection in the real world. And people have already developed various techniques to measure the signals much smaller than this. On the other hand, this terahertz frequency has a wide application in various areas, as the existing electric devices based on electric transport, such as transistors, have in principle a limit at 300 GHz. We could also imagine by using the switching of magnetic skyrmions at the source to generate a terahertz electric signal, which may be very promising to future applications. Until now, even frequencies in the terahertz range are still hard to extract, and the prices of such equipment are far away from budget-friendly. We could firmly believe nothing will be a stumbling block and we are stepping towards the terahertz era. Then, if we vary the film thickness from 30 to 70 nanometer, we could find 2 Bloch-points will create during the skyrmion annihilation process, rather than just only one. Because there are two Bloch points moving towards opposite directions, the generated electric field will superimpose and will result in a quite messy signal, especially when the two Bloch points have different velocities or phase shifts. More generally, any non-uniformity, such as local non-magnetic defects, polycrystalline grains, will tend to make the phenomena much more complicated. So, if we want a uniform matter-magnetic transition, what can we do? By engineering a notch, local modifications of magnetic parameters can be achieved by various techniques, such as focused ion beam with the irradiation of gallium ions. Here we simulate a conical non-magnetic region near the top surface with 5 nm depth and 10 nm diameter. The magnetization would form a vortex around the conical notch. And when we calculate the distribution of the magnetostatic energy with respect to the computational layer through the film, and use the energy at the bottom surface as a reference layer, and when the thickness is comparatively thick, we have the maximum energy near the middle layer. That's why the skyrmion tube breaks inside the film. However, a notch structure would effectively modify the local magnetostatic energy, and kind of shifts the distribution towards the top surface, makes the texture more fragile in energy. Then you may have already guessed what would happen. Yes, only one Bloch point, and to be born from the notch. By switching the magnetic field, we could easily nucleate and annihilate a metastable skyrmion against the effect of non-uniform energy distribution. And more importantly, a very pretty figure of Bloch-point dynamics. Here's a comparison of the Bloch-point creation with respect to the film thickness. No matter how thick the sample is, at around 1.3 Tesla, one Bloch point will nucleate from the top surface with the presence of the tiny notch. Here are some take-home messages. First, we visualize the annihilation process of the single skyrmion. By applying a magnetic field, the mechanism is dominated by the Bloch point creation, propagation, and annihilation. And we predict the motion of the Bloch point will generate a strikingly high emergent electric field, with the magnitude in the order of megavolts per meter, modulated by the frequency in the range of terahertz, and such signal may be possible for detections, such as using the prompt pole experiment. Then, in order to pave the way of experimental validation and even future application, we propose the feasibility to artificially control the Bloch point dynamics. We aim the reverse side of Bloch point creation, which may end up with a much better performance for skyrmion-based devices. That's all I'm going to show you today. Thanks a lot for your time. If you are interested to this video or have any questions, please leave messages or contact us by email. You may also know more details about what we are doing now by visiting skyrmionics.org or just scanning the QR code. See you next time.